So dear all, so today's topic is Magnitude Comparator, which is one of the important topic in combinational circuit. So Magnitude Comparator, it compares two inputs. So let us consider A and B. So it compares A input and B input. It produces three outputs. They are A equal to B, A greater than B, and A less than B. So this is our problem statement. You have to compare two inputs A and B of length 1 bit, 2 bit or 4 bit, etc. So we are going to see about n-bit magnitude comparator. So it compares A and B and produces three outputs. The output may be either equal or greater than or less than. So let us consider, we will design 1-bit magnitude comparator. So 1-bit magnitude comparator, A is 1 bit. Let us consider A naught, and B is also 1 bit, right? So A is 1 bit and B is 1 bit. A and B may have the combination, both may be 0, 0, 0, 1, 1, 0 and 1, 1. So as we already discussed, it will have three possible outputs. A equal to B, A greater than B, and A naught less than B naught. So now compare A naught and B naught. So here first combination 0, 0, both the inputs are 0, 0. So A naught is equal to B naught, the output is 1, whereas other output it is 0. Next, the value for A naught is 0, the value for B naught is 1, which means that the value of A is less than the value of B. So A naught is equal to B naught will have 0, A naught greater than B naught will have 0, A naught less than B naught will have the value as 1. Similarly, 1, 0, the weight value of A naught is 1, whereas the weight value of B naught is 0. So A is greater than B, other output the value is 0. The last combination, both the inputs are 1, 1. So naturally, A naught is equal to B naught, the output is 1, whereas other combination, the output is 0. Now we have to design a logic circuit. So we have formulated the truth table. Now from the truth table, you have to find the output expression. So if you analyze the expression for A naught is equal to B naught, it is equivalent to X naught function. So A naught is equal to B naught for this output. Corresponding output is A naught, X naught, B naught. Similarly, the value for expression for A naught greater than B naught is A naught greater than B naught, the output is 1. For the combination, A naught is 1, B naught is 0. So corresponding expression, A naught is 1, B naught is 0. So we can write A naught into B naught bar. The last one is A naught less than B naught. A naught less than B naught, the output is 1. For the combination, A is 0 and B is 1. So the corresponding expression is A naught bar into B naught. Finally, you have to draw the logic diagram. So logic diagram, you will have the inputs A, B, the A is in complement form. Similarly, I am writing. So this value represents A naught. This value represents A naught bar. Similarly, this value represents B naught and this one is B naught bar. So now we have to draw the logic diagram. So logic diagram, so this one A naught, B naught, I am taking the signal and connecting to a XNOR gate. The output is A naught is equal to B naught. Similarly, for A naught greater than B naught, I have to take the true value of A naught and complement value of B naught. So I have to use an AND gate. So the value for A naught greater than B naught is A naught into B naught bar. Similarly, the value for the expression logic design for A less than B. So A less than B, I have to get complement value of A and true value of B. So true value of B and complement value of A, put your AND gate, the output is A naught bar into B naught. So this represents A greater than B and similarly this represents A less than B. So I hope everybody do understand what is 1-bit magnitude comparator. Now we will move on to 2-bit magnitude comparator. So let us consider 2-bit magnitude comparator. So 2-bit magnitude comparator, we have seen already 1-bit magnitude comparator which compares A naught and B naught. So 2-bit magnitude comparator compares A1 A naught with B1 B naught. Now A is 2-bit. Similarly, B is also 2-bit. So I am comparing A and B where A is 2-bit and B is 2-bit. A is represented as A1 A naught and B is represented as B1 B naught. So totally there are 4 inputs. So if there are 4 inputs, you will have the combination size is 16 combinations. So you will have 3 outputs. A naught is equal to B naught, A naught greater than B naught and A naught less than B naught. So the combinations are 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, etc. The combination goes up to 1, 1, 1. So if it is 2-bit magnitude comparator, totally there are 4 inputs A1, A naught and B1, B naught. So you may have up to 16 combinations. So it is possible to write the truth table for 16 combination and you can analyze the output equation. Let us consider you want to design 3-bit magnitude comparator. So 3-bit magnitude comparator, A is 3-bit. Let us consider A1, A2, A1, A0. Similarly, B is also 3-bit, B2, B1 and B0. So the total number of input combination is, you all know that, so number of input variable represents the number of combinations. So there are total number of inputs is 6. So 2 power 6. So 2 power 6 is 64 combinations. So is it possible to write 64 combinations? Then you have to find the output equation and you have to go for simplified equations. For example, if I want to design 4-bit magnitude comparator. So in this case, A is 4-bit, A3, A2, A1, A0. Similarly, B is also 4-bit, B3, B2, B1 and B0. So total number of inputs is 8. So total number of combination, so you all know that 2 power 0 is 1, 2 power 1 is 2, 2 power 2, 4, 2 power 3, 8, 2 power 4, 16, 2 power 5 which is equal to 32, 2 power 6 is 64, 2 power 7 is 128 and 2 power 8 is 256. So for a 4-bit magnitude comparator, you have to write all the 256 combinations. Then you have to go for output expression. So it's a very complex task. So we can do it directly by comparing the logical values. So in this session, we are going to write the equation directly instead of going for truth table, then finding the expression, then drawing the design. Instead, we are going for direct derivation of expression. So let us consider 2-bit magnitude comparator. So for any number of bits, if A is equal to B, the corresponding expression is XNOR function. Because XNOR truth table, if both the inputs are equal, the output is 1. So for any number of bits, if A is equal to B, the corresponding logic expression is equivalent to XNOR function. So A is equal to B, the output expression can be written as A1 XNOR B1 into A0 XNOR B0. So this is XNOR function. So for any 2-bit magnitude comparator, if A is equal to B, the corresponding expression is A1 XNOR B1 and A0 XNOR B0. So let us consider, for simple understanding, A0 XNOR B0 is equal to X0. Similarly, A1 XNOR B1 can be written as X1. So, A is equal to B is equal to X1 into X2, where X1 is A1 XNOR B1 and X2 is A0 XNOR B0. Now, let us consider for the output A greater than B. So, how do you say that A value is greater than B? Simple, you just scan from the most significant bit. So, the most significant bit should be 1 for A and 0 for B. So, we can write the expression as, so A is A1, A0. Similarly, B is B1, B0. You are just scanning the input values. So, by scanning the input values, A1 should be 1 and B1 should be 0. So, we can write the expression directly. A1 is 1. So, A1 is 1 true value. B1 is 0. So, 0 is represented by bar. So, this is first possible use case. Second case is, for example, A1, B1. Similarly, A0, B0. So, second possible condition is A1, A0, B1, B0. So, as I have already said, scan from the most significant bit. So, if the most significant bit is 1, 1 or it can be 0, 0. So, if both the bits of A1 and B1 are equal, move to the next bit, that is MSB minus 1 bit. So, in this case, for A greater than B, A0 should be 1 and B0 should be 0. So, if you see 1, 1 is greater than 1, 0. Similarly, 0, 1 is also greater than 0, 0. So, you can write the expression as, so the MSB bits are equal. If the MSB bits are equal, the corresponding function is XNOR function A1 XNOR B1. So, A1 XNOR B1 we have already represented as X1. So, X1 into A0, A0 is 1 and B0 is 0. So, corresponding expression is X1 into A0 into B0 bar. Similarly, we will move on to the third expression. So now we move on to the next third expression. So third expression is A less than B. So again we are taking two bits A1 A0, similarly B1 B0. Scan from the MSB bits of A as well as B. So if the MSB bit of A is 0 and MSB bit of B is 1, we can directly write the equation as A1 bar into B1. So MSB bit of A is 0, MSB bit of B is 1. Now the second possible use case. So here whatever may be the value for A0 and B0, if the MSB bit of A is 0, MSB bit of B is 1, we can directly write the equation as A1 bar into B1. Now the second case. So second case, if both the bits are equal, it may be either logic 0 or it may be either logic 1. So if both the bits are equal, if A0 is 0 and B0 is 1. Similarly, second condition, A0 is 0, B0 is 1. So 0, 0 is less than 0, 1. Similarly, 1, 0 is also less than 1, 1. So we can write the expression as, so here the MSB bits of A1 and B0 are equal. Corresponding expression is x1, where x1 represents A1 x0 B1. So x1 into A0 bar into B0. So instead of getting into the truth table, writing the expression, we can directly write the expression based on the logical analysis. Right. So we have already seen 2-bit magnitude comparator. In a similar manner, we are going to design a 4-bit magnitude comparator without writing the truth table, expression and logic design. So let us consider 4-bit magnitude comparator, which consists of two inputs A and B. A is of length A3, A2, A1, A0. Similarly, B3 is of length B3, B2, B1 and B0. So as we have seen earlier, for 2-bit magnitude comparator, we are getting into the equation of 4-bit magnitude comparator. So A is equal to B, that is A3 XNOR B3 into A2 XNOR B2. Similarly, A1 XNOR B1 and finally A0 XNOR B0. So this equation can be written as x3 into x2 into x1 into x0, where x3 is equal to A3 XNOR B3, x2 is equal to A2 XNOR B2, x1 is equal to A1 XNOR B1 and x0 is equal to A0 XNOR B0. Now, A greater than B. So A greater than B, as we have discussed earlier, scan from the MSB. For A greater than B, A3 should be 1 and B3 should be 0. So this bit should be 1, this bit should be 0. So we can write the expression as A3 B3 bar plus second condition, if the value of A3 and B3 are equal, you have to check the next MSB minus 1 bit. So A3 B3 equal, for A3 equal to B3, corresponding function is A3 XNOR B3. For better simplification, we are just saying it as x3. So x3 into So now A2 bit is 1, B2 bit is 0. So A2 bit is 1, so we can write A2 B2 bar. Now let us consider the first two bits of A and B are equal. So first two bits, which means A3 is equal to B3 and A2 is equal to B2. So I can write X3, X2. Now A1 should be greater than B1, which means that A1 is 1 and B1 is 0. So A1, B1 bar. And finally, let us consider the first three bits of A is equal to first three bits of B. So I can write X3, X2, X1 because first three bits are equal. Then the last bit of A should be greater than that of last bit of B, which means that A0 is 1 and B0 is 0. A0 is 1 true value and B0 is 0. And finally, the last equation for 4-bit magnitude comparator, A less than B. Now scan from the first bit. So for A should be less than B, the value of A should be 0, the value of B should be 1. So which means that A3 bar B3. First condition satisfied. Now second condition. The first bit of A is equal to first bit of B, which means that I can write A3 X nor B3, that is X3 into first bit of A is equal to first bit of B. Now scan the next bit, that is A2 bit and B2 bit. So A2 bit should be 0, B2 bit should be 1, which means that A2 bar into B2. Now the third condition, the first two bits of A is equal to first two bits of B. So which means that X3 into X2, where X3 represents A3 X nor B3 and X2 represents A2 X nor B2. So first two bits of A and B are equal. Now I have to check the third bit. So third bit is A1 should be 0 and B1 should be logic 1. So A1 should be 0 and B1 is 1. Finally, the last condition, the first three bits of A and B are equal. So X3, X2, X1. If the last bit of A is 0 and last bit of B is 1, we are calling it as A less than B. So now we have derived the expression for A greater than B, A less than B and A equal to B. Similarly, you can design for any n-bit magnitude comparator, right? And I hope all of you understand this session. Thank you.